Thank you.
Thank you, Fran, and thank you for the attendees who asked questions. We're going to move on to our next speaker. So our next speaker is David Nagel of the George Washington University. Dave has worked at the Naval Research Laboratory for 36 years and has been at the George Washington University for 21 years. I have been fortunate to have the privilege to conspire with Dave in many activities. Dave's invited talk is 20 minutes and is titled Input, Stimuli, and Output Signals in LENR Experiments. Let's hand it over to Dave.
Thank you very much, Steve. I ask if you can hear me and see the graphics.
Yes, we can.
Okay, thank you. So as the title says, we're going to talk about input stimuli and output signals. And the purpose of this presentation is to draw attention to particular past LENR experiments and to suggest some attractive future LENR experiments. I've been involved in the field since the day after the March 1989 Fleischmann-Pons press conference, developed some viewpoints on what's worthwhile, and I appreciate the opportunity to share them with you. So if you're going to do LENR experiments, you only need three things: the experiment and something to excite it and something to measure what comes out. And over the decades, a wide variety of stimuli have been put into and diverse signals been measured from LENR experiments. And that brings up a couple of questions. One can ask, of all the published inputs and outputs, which might be most valuable to emphasize in future experiments? And then beyond that, what other stimuli or signals might be used to further both the goals of the field, the understanding and the commercialization of LENR? So that's basically what the talk is about. This is the architecture of this presentation. At the top is the main focus, the LENR experiment. Might include electrochemical or hot gas or plasma loading of various metals and alloys with either protons or deuterons. And then below on the left are the input stimuli, and on the right, the output signals. And they fall into categories. The weak lavender color indicates energy and matter that goes into or out of the experiments. Then in the orangish color, the next two lines, you have lumps, neutrons or particles. And then in the yellow, there are the various regions of the electromagnetic spectra indicating photons that can go both ways. In green, you have sonic and ultrasonic work. And then finally, various fields on the bottom, including electrical impulses and electrical noise. Now, it'd be great fun to go through each one of the listed ones, which indicate that something has been done, and also to look at the blanks, which, as far as I know, are blank because there hasn't been work in that area. In other words, as far as I know, gamma rays have not been put into an LENR experiment. Might not be worthwhile, but it's something to discuss. So the talk has two parts. First, we'll deal with the input stimuli, and I will limit myself to the four shown here in red: high temperatures, visible light, terahertz radiation, and make a strong point about electrical impulses. Okay, so starting with the high temperatures, this is a graph from the colleagues at Tsinghua University. I thank Professor Lee and the others. You have four graphs. In each one of them, the inverse of the absolute temperature is horizontal and the log of the excess power is vertical. So there are plots where an experiment that obeys an Arrhenius law, that is, has an activation energy, the main term is shown in the yellow boxes, plots out as a straight line, and you see there are 6 of them here. So in the upper left-hand corner, you have data from Fleischmann, from Ed Storms, and an experiment done at Tsinghua. Upper right is Dennis Lett's experiment. Lower right, Mizuno-san, and then on the lower left, Parkhomov's excess power data. So there are 2 things to carry away from this. One is low temperatures, that is to the left on this graph, because it's 1/T, favor the production of LENR. And secondly, it's an activated process, according to these data. And the activation energies range from a low of 0.14 electron volts in the case of Ed Storm's data to, I think, the high is the 0.949 activation energy that Dennis Letts obtained. So guidance to experimentalists: use high temperatures. Then a challenge to theoreticians is to explain the range and the specific activation energies involved. So this is a very rich set of data that needs further attention as far as I'm concerned, as well as replication. Oh, by the way, in the top right corner, you'll see yeses and nos, and they're meant to indicate whether or not an experiment has been replicated. So this shows, of course, these temperature variation experiments have been replicated. Now, moving on to the photon input. This is data from the Dennises, Letts, and Cravens, published in 2004. Horizontally, you have time, and vertically, the excess power in milliwatts. The point of this is that they were running along essentially without excess power and turned on a laser, a 30 milliwatt laser, not all of which was absorbed, of course, in the cathode. And it led over time to a 500 milliwatt increase in LENR power. Laser turned off, power declined. Laser turned on, power increases. So this has been replicated a few times, but it still is a approach to LENR experiments that deserves attention because it has a dramatic effect. And I'm unaware of any experiments that are being done right now that include laser excitation. I'd be happy to learn about them. Staying with electromagnetics, this is work from Peter Hagelstein and again, Letts and Cravens. On the horizontal axis is the frequency of the radiation they put onto a cathode in an LENR setup. They could vary the frequency by beating two lasers against each other to get the terahertz radiation. Vertically is the excess power in milliwatts going up to around 300 milliwatts. And you can see clearly that phonon generation using photons, that is photon to phonon, provides a means of controlling LENR rates. And two of the peaks match the phonon frequencies in palladium deuterium. So this is clearly important scientifically because it indicates the importance of phonons in generating LENR. Whether or not it will provide a practical means of controlling the output of LENR generators is to be determined. Okay, so now I have three graphics on electrical impulses. This is a famous graph from Energetic Technologies. Time horizontally and power vertically on a dramatic scale. It goes from 0 watts up to 40 watts. The black line is the input power. The red line is the output power, peaks at 34 watts. Okay, amazing. A couple of years ago, I was looking at this and I realized there were alignments between some of the, call them what you will, changes, glitches, hiccups in the input power, which is generally at the level of a watt or so, and the behavior of the output power. So for instance, at B, there's a negative excursion in the input, which would indicate a deloading, a flux of neutrons going out of the material, which led to a dramatic increase in the output power. Similarly at C and other places. I could spend a lot of time going over this, but it said to me, Dave, look at the details of the input power and experiments to see if there's something that might be useful. So I turned to the similar data from the Naval Research Lab. Again, time going to the right, power in watts up to 10 watts. And if you look at the green input line, you'll see there are little steps, small steps, much less than 1 watt, that sometimes, but not always, lead to steps in the output power. Okay, so again, these data deserve much more time and discussion than is necessary here. But the point I'm trying to make is clear that one can consider willfully put into LENR experiments electrical impulses. And, you know, I know early on Takahashi had the square wave input output. There have been, of course, the Q pulses from Brawan, and this is not a clean slate. But given the data that I just showed you, it seems worthwhile to configure an electrochemical cell so that you have a DC power supply that runs the electrochemistry through a switch A, and then at some time you open A so you don't fry the power supply, and switch on a pulsar supply that could produce additional excitation in the cell. Alternatively, at the bottom it says a coil could be put across the electrochemical leads and subjected to a current pulse to introduce a pulse into the cell. So I hope that the data that I just showed you, the other work in the field that's related to it, and this possible experiment lead to experiments that involve more pulsed excitation of LENR cells. Okay, so turning to output signals, I'll take time to talk about two of them, infrared radiation and sound. I would dearly like to have time to talk about magnetic fields and electrical noise and other things, but that'll be covered in the paper that accompanies this presentation. An open question is whether or not the things that I'm talking about for electrochemical experiments carry over into hot gas and plasma loading experiments. That's another question. So this graphic shows two experiments from the Speywer lab, Stan Spock, Pam Mauzier-Boss, and Frank Gordon. On the left is an infrared image that from a co-deposited palladium deuterium showing hot spots, little white speckles on a warm cathode. And on the right is a sound measurement, time running to the right for 2 seconds, the duration of this graphic, and the sound picked up by a piezoelectric transducer shown vertically. And as far as I know, neither of these experiments have been repeated, and they call out to me for attention because they give very detailed information in space and in time about what's going on, at least in these co-deposition experiments. Whether or not they would carry over to other electrochemical experiments is an open question. Okay, so you probably noticed that some of the entities in this table are both input and output. I'll finish up by talking about radio frequency radiation that has served both as input stimuli and as output signals. This is information from an early paper by the Bacchus Group, 1993, including Dennis Letts. In the left is a cartoon that shows their electrochemical cell with a coil wound around it that was could be excited by an RF generator. And on the right is a scan of frequency that they did from around 70 megahertz to almost 600 megahertz. And excess power is plotted vertically up to about 2.5 watts. And the data clearly show that the input radio frequency has a significant effect on the ability to generate excess power. Okay, and that is a relatively simple experiment. And as far as I know, again, I'd be happy to be corrected, but I don't know that that's been repeated. And that calls out to me for further attention. Now, staying with RF, both inputs and outputs, this is a graph from a review we did 5 years ago. The graphic on the top goes from 10 to the 7th up to 10 to the 11th hertz. Above the green line is a situation where RF is put into an experiment, the Bacchus experiment that I just talked about. And below the green line are indicated experiments where people measured the RF coming out of LENR experiments. And you see the ranges indicated by the red lines, and the dots indicate specific frequencies that were seen. So does the RF generation correlate with excess heat generation? No, but it's an enticing indicator that something at a very high speed is going on in these experiments. And when you look at what's possible, only the double layer at the surface has the small dimension that might be spanned in the kind of times that are necessary for RF generation. So this is an enticing experimental tool, as well as another challenge to experimentalists. Since we did that review, Mitchell Schwartz produced 3 papers on RF emissions. He observed a 3.27 megahertz line. It's at this energy, the red arrow at the bottom of the graph in the top. And I can't summarize his papers here, but I invite your attention to him. That's very nice work that deserves further consideration. So in closing, I would emphasize that, I have a lot of colleagues, Schwartz among them, who have put out remarkable experimental results, and they deserve attention. They should have been and will be included in the paper in this particular study. I would advertise the need for use of more modern instrumentation, especially synchron radiation. There have been relatively few experiments, and I don't know of any experiments where an LENR cell was taken to a neutron facility that has the ability to observe the protons and the deuterons because of the mass of the neutrons being similar. Need more parametric experiments in which the inputs are scanned over very wide ranges. They are particularly valuable. And then finally, there's a need for, you might say, a flip companion to this study, new experimental designs that are aimed at testing particular ideas. There are lots of ideas about in our field, experimental and theoretical ideas, and experiments that are designed specifically to test them, whatever the input stimuli or the output signals are attractive to me. So in conclusion, let me thank you for your interest and look forward to any questions you might have.
Thank you, Dave, for a very engaging presentation. So we do have time for some questions. So raise your hand, go to the reactions button at the bottom of the screen if you wish to do so. Luciano, you have a question? Go ahead.
Thank you, Professor Nagel, for your presentation of your work. And just first a comment, and I had a paper from the NASA team where they used gamma rays to induce fusion in titanium and erbium, deuterated titanium and erbium. And do you think it's possible that the key is lattice strain? So all of those methods are solutions to strain the lattice so that the effects start to occur. What do you think about this?
Lattice strain, I believe, is A, important, but B, not the key element. I'll say in a talk tomorrow that I think that there are two main things, both of them requirements to produce LENR, adequate concentration of the reactants on one hand, and then motion. If you just have reactants sitting there, what are they going to do? They don't necessarily react. They're not near each other. But if you have a flux or vibrations, then you have the possibility of interactions. So strain is important. The lattice spacings are important, but I don't think they're the pivotal explanation of LENR. And if you'll send me that paper, I'll greatly appreciate it. There are so many papers in this field, I'm bound to miss something. So I would greatly appreciate that, Luciano.
Luciano, thank you for your question. Jenny, you're next. As soon as you're unmuted, you can go ahead. It looks like you're good to go.
Thank you very much. Mr. Nagel, I don't connect with your thesis. It needs new experiment designs. In my opinion, it needs a new paradigm of natural science, because the experiments in all kinds of fusion, like tokamak and low energy run during so many years, and we have no good results. Thank you very much.
Well, I agree that we are in fact dealing with a new paradigm in nuclear physics. There's to be no question about it. The interactions of nuclei on and in lattices are different than what has been studied for the better part of over a century now. So I firmly believe that once we understand LENR, the subject of nuclear physics and nuclear technology is going to be dramatically different than it is right now.
Yeah.
Thank you. If there are any other questions, we do have about 1 minute. I'll give it a few seconds to see if anyone has anything to add. If not, we can proceed to the next